All right, so let's talk about intermolecular forces. These are attractive forces between molecules. Attractive forces between molecules. We have talked about attractive forces between atoms. Those are called ionic bonds and covalent. Ionic and covalent. Attractive forces between atoms. So if, let's say I have water here. So that would be forces right here. All right, this hydrogen is attracted towards this oxygen. What this is about this water molecule being attracted to another water molecule. It's attractive forces between molecules, not between atoms, between molecules. That's what we're looking at, okay? So there is a difference between attractive forces between atoms and attractive forces between molecules. There are three types we're going to talk about. One is called a dispersion force. You might have learned it as van der Waals forces. You might have heard that term, van der Waals. If you haven't, don't worry about it. Or London dispersion forces. We're also going to talk about dipole-dipole forces. And then the last one, which is the daddy of them all, which is hydrogen bonding, okay, which is very good in biological systems. Okay, the first one that your book talks about is dipole-dipole forces. So we will talk about dipole-dipole forces. These are attractive forces between polar molecules. So imagine you have a polar molecule, let's say like BRF. Let's say you have bromine attached to a fluorine. Okay, this is a polar molecule. How do I know? Fluorine is more electronegative than bromine, so I have a pole this way. So this fluorine has what's called a partial negative charge, and the bromine has a partial positive charge. This kind of symbol is a delta symbol. It's a short lowercase delta. Okay, and then I put either a negative or a positive telling me where the electron density is. Okay, so the dipole is towards the fluorine. So fluorine has more of a negative charge around it, and bromine has more of a positive charge around it. So what happens is this fluorine is attracted towards a bromine of another molecule. All right, this fluorine is attracted to another bromine of another molecule. Okay, and then this bromine is attracted to another fluorine of another molecule. All right, and you have a network of these interactions. You can kind of see here, there's attractive force here, here, here. All these are attractive forces right here. There's an attractive force, attractive force, attractive force, attractive force. So you can see the blue ends are attracted towards the negative ends. And you have all these forces all in between. You have a network of these forces which keep these molecules together. They keep them together, okay? So in solids, these atoms are closer to each other. These attractive forces are stronger, all right? In liquids, they aren't as strong. And in gas, you don't have them anymore. So what determines a boiling point of something is how strong these forces are, okay? The stronger the forces, stronger intermolecular force, or IMF is what I'm calling it, right? The larger or the higher the boiling point. It means it takes a lot of energy to break these bonds to cause them to separate from each other and turn into the gas phase. Okay, so this is what a dipole-dipole force. It's between polar molecules or polar bonds, and you have this alternating positive and negative force to each other. Okay, so determine whether or not these molecules will have dipole-dipole moments. Okay, so let's talk about bromine. Bromine, you have a bromine attached to a bromine. Well, first of all, is this polar or nonpolar? This is a nonpolar molecule. So right off the bat, I can tell you that this does not have a dipole-dipole. Okay, so no dipole-dipole force. All right, so here, we'll just go here. The molecule contains no dipole since both atoms are identical. It's a nonpolar bond. All right, here the molecule is bent where the dipole for each bond does not cancel out, making this a polar molecule. So that means, yes, there is dipole-dipole. The molecule is symmetrical and the dipoles for each bond cancel each other out, making it nonpolar. Okay, so first of all, so there's the Lewis structure of it. Okay, so and then here it tells you if there's dipole-dipole. So let me go back here. Bromine is nonpolar, so there is no dipole. No dipole-dipole. This is polar, so therefore there is dipole-dipole forces. Since these all cancel each other out, technically this molecule is nonpolar, so there is no dipole. Okay? The next one I want to talk about is a special type of dipole, which is called hydrogen bonding. Hydrogen bonding is very strong. It's one of the strongest of all these forces, and it's a special type of dipole-dipole. All right, it happens between a nitrogen hydrogen, oxygen hydrogen, or a fluorine hydrogen bond. All right, really there are two things you need. The two things is a polarized hydrogen, and the second thing is a lone pair. Oh. Lone pair. Okay, so like water, for an example, you have hydrogen bonding. In fact, you have one of the strongest hydrogen bonds. So these lone pairs, all right, are attracted towards the hydrogen, the polarized hydrogen of another molecule. All right, these are attracted towards a hydrogen. These are attracted towards an oxygen lone pair, and so forth and so on. Okay, and these are very strong interactions. Okay, so this is a good example. See the CH2F2? This is the structure of CH2F2. And would there be hydrogen bonding? And the answer is no. There's no hydrogen bonding because this is not a polarized hydrogen. Now you might say, well, didn't you just say hydrogen and fluorine? Yes, that's a hydrogen fluorine where the hydrogen is on the fluorine and it's polarized. You have a partial positive side. These, remember I told you, hydrogen and carbon are equal in electronegativities. So there is no polarization on there. So there's no no hydrogen bonding. This one does, and this one most likely will, but probably not too much because it's pretty small. Okay, so it says here no hydrogen bonding because it doesn't contain. That's totally not true. You kind of have to have a polarized, but usually it does occur between nitrogen, oxygen, and fluorine. Okay, so as far as I'm concerned, that one, the H2SE, the answer is yes or no, as long as you can explain to me why or why not. Okay. And then finally, the last one is the weakest of all of them, and that is a dispersion force. This is between non-polar molecules. Sorry, I'm trying to lower down the, so you can see it. There we go. So this is a dispersion force. These are the weakest. This is between non-polar molecules. What kind of happens is, so like, let's say we have a bromine and a bromine, non-polar. All right, there is this electron cloud that's around our two bromines. All right, and what's happening is this electron cloud is not stagnant. It's actually swifting back and forth. Perfect analogy is imagine you have a bucket of water and you kind of shake that bucket a little bit. The water kind of sloshes back and forth, back and forth, back and forth, until eventually it stops. That's what's happening here. The electron density is swishing back and forth, back and forth. At one moment in time, you have kind of this more electrons on one side of the bromine, so it gives this side more of a partial negative and this side more of a partial positive. Then at the next moment, they swash the other direction, and you have more of a partial negative on this side and a partial positive on that side. So you can kind of see down here how it's kind of changing. You have some that are polarized and some that aren't. Then they kind of swoosh back and forth. You got others that are polarized, some aren't. And then the ones that were polarized are no longer polarized, and the ones that weren't polarized are polarized. And this is what's happening. It's kind of changing back and forth. They're kind of shifting. It's not like it's always polar or always non-polar. They kind of just swish back and forth. All right, and it's what's called an induced dipole, because what happens is, let's take this molecule. This molecule has a partial positive here and a partial negative here. So what it's going to do is it's going to affect this molecule next to it. It's going to induce the electrons to kind of flow more towards this direction because you have more of a positive side here. So you have a positive at this end, so this molecule, the electrons are going to start being attracted towards that positive end and kind of now start forming a partial negative positive. That's what's meant by an induced dipole. All right, same thing here. This is a partial negative side. It's going to cause the electrons to kind of go away and kind of now make this into a partial positive, which is what it's being shown over here. So that's what induced means. It's causing this shifting back and forth. Okay, so you basically have, I'm going to write down here some notes here. You have your dispersion, which is the weakest. Okay, this is between non-polar. And then you have your dipole-dipole, which is between polar molecules. And then finally, you have hydrogen bonding, which for the most part is being hydrogen-nitrogen, hydrogen-oxygen, and hydrogen-fluorine. Okay, so I hope this makes sense. There's some other information here, which we'll talk about in class. We don't have to talk about it right now, but if you'd like to read it, obviously, please feel free to go ahead and read it. But we will talk more about this in class, and we will kind of go over some of these pointers. And I just realized there's kind of a review here. I just talked about this, that dispersion forces are the weakest. Dipole-dipole are next and strongest, and finally hydrogen bonding. This also says that the weight of the molecule has nothing to do with boiling points. All right, the boiling points have nothing to do with the mass of the molecule. This is the reason for boiling points. Water is one of the lightest molecules in nature, 18 grams per mole, and it has one of the largest boiling points. Okay, well, how can something so light have a largest boiling point? Well, it's because it has one of the strongest intermolecular forces. Okay, so that pretty much sums up chapter 6. If you have any questions, please bring them to my attention and we will talk about them in class. This is a really good problem that you might want to do. It just says what kind of intermolecular forces. So you can go ahead and look at the slides that I posted, and I will see you in class.